All right, we're into one of the last sections of the chapter, and today we're looking at absolute value and quadratic one variable inequalities. So the nice thing about these is they are very similar to the quadratic and absolute value equations we did in the beginning of this chapter, but there's a few slight differences. All right, so your first step is the same as if it was an equation. So the first thing you want to do is isolate the absolute value symbol. And remember, you do that by undoing. So PEMDAS backwards. And then, just like the equations, you're going to make two separate inequalities now. So a lot of similarities still. Inequality 1, you're dropping the absolute value symbol and keeping everything else the same. So just like the equation, but you have an inequality instead. And then inequality 2, you're going to drop the absolute value symbol. You're going to make the non-variable side negative just like we did for the equation, but the difference is you also have to change the direction of the inequality. All right, so that's the real only difference so far. So if we look at our first example here, I have x plus 2 is less than 2. The absolute value is already isolated, so I'm going to go and make two inequalities now. First one, drop the absolute value, keep everything else the same. Second one, drop the absolute value, flip my sign, and make the right side negative. All right, so you're going to solve for x and write two inequalities. All right, so I'm going to subtract 2 and get x is less than 0. Subtract 2 and x is greater than negative 4. All right, now we're going to graph these on a number line. So here's going to be 0, negative 1, negative 2, negative 3, and negative 4. So I have an open dot at 0, and I'm saying, and an open dot at negative 4. So I'm saying x is less than 0, x is greater than negative 4. So less than 0 is going this way, greater than negative 4 is going that way. So my shading is in the middle. All right, so now we have a little bit more to clean up with our algebraic solution. So if the shading is in the middle, add the word and in between the inequalities, or you can write as one inequality, such as like we do domain, negative 4 is less than x, which is less than 0. If the shading is on the outside, add the word or in between the inequalities. So since the shading is in the middle, I can add the word and in between. And the reason we're adding the word and in between is because my solution is only in this region. These numbers in this region are less than 0 and at the same time greater than negative 4. So that's why we're using that word and. Now again, we could also write this as a compound inequality, like a domain. You don't have to have both, but if we wanted to, whichever one you like better. If I'm doing a domain, the farthest left is negative 4, is less than x, is less than 0. So either of these answers is acceptable. All right, let's try example 2. Again, I'm trying to isolate that absolute value first. So I'm going to add 2. Because PEMDAS backwards, I'm undoing addition, subtraction. And then I'm going to undo multiplication, division. So divide by 8. And so now I want to undo that absolute value. So this is where I'm going to write two separate inequalities. So drop the absolute value, keep everything else the same. Drop the absolute value, flip my sign, and make my right side negative. And so now I also have to divide by negative 2. So I'm going to get x. I'm flipping my sign here because I'm dividing by negative. So x is less than negative 2. And then x flip my sign, greater than positive 2. I'm running out of my room for my number line, so I'm going to put my number line up here. So 2, 1, 0, negative 1, negative 2. All right, so let's take a look at what we have here. I have an open dot, 2, open dot at negative 2, and I am saying that x is less than negative 2. It's going this way. X is greater than positive 2, going this way. And so since the shading is going outwards, I need to add the word or in between, because the shaded region over here is less than negative 2 or greater than 2. It's not both at the same time. So in this case, it's greater than 2. And over here, it's less than negative 2 or greater than 2. In this case, it's just less than negative 2. So it can't be both of the inequalities at the same time. It's impossible for one number to be in both shaded regions at the same time. All right, as we look to example 3, again, I'd add 4. I'm going to undo the absolute value by making 2 inequalities. Okay, so first one, just drop the absolute value symbol. Second one, dropping the absolute value, flipping my sign, making the right side negative. Add 17. And then divide by 2. So we get x is greater than 13. So I'm going to add 17, which would be 8, divided by 2. X is less than 4. All right, I have some space for my number line here. So I'm just going to do 4, 13. All right, open dots on both. So I need x to be greater than 13. X be less than 4. And so the word or again would come into play, because I can't have one single solution be in both of those regions at the same time. All right, now on to graphing our quadratic 1 variable. So you're going to solve for x by factoring and using the zero product property. You're going to get 2 answers, and these are going to be your boundary points. And for right now, just treat them as like an x equals, because we'll plot the boundary point. All right, so remember, in order to factor, I have to get it equal 0, so I'm going to subtract 12. We have 2x squared minus 5x minus 12 is less than 0. So don't forget all of our factoring. We look for a GCF. This one doesn't happen to have a GCF. I have 3 terms with a number greater than 1 in front, so I have to do my slide divide bottoms up. All right, so what multiplies to 24 and adds to negative 5 would be 8 and 3, negative 8, positive 3. And it does say solve for x, so for right now I'm just going to say x is equal to 8. And I actually like to leave a space here because I know I'm going to have to put my inequality in here. And x is blank, negative 3. So almost maybe put like a little dotted box in here, because you have to put your inequality symbols in here coming up. You're then going to plot the boundary points on a number line. Here's 8, here's negative 3. You're going to pick a test point and then shade the correct part of the number line. So I usually like to test x equals 0. You just have to be careful, because remember, a true statement means that value should be shaded. A false statement means that number should not be shaded. So in this case, 0 happens to be in the middle. So if I test x equals 0, I would get 2 times 0 squared minus 5 times 0 is less than 12, or 0 is less than 12. In this case, that's a true statement, so 0 should be shaded. So I'm going to have an open dot at -3, open dot at 8. 0 made a true statement, so I'm shading in between. If 0 was outside of my boundary points and it was a true statement, then guess what? I shade outside. So your shading is always either going to be in between or pointing in both opposite directions. So now that we have the graphic solution, we're going to go back, look at the shaded number line, and write your algebraic solution using the correct inequality. So now I need to figure out what inequality is going to go here. So if I'm looking at the 8, it's shading less than 8. So I'm going to go less than. There's no equal to, so it's just less than. And then here's my -3. It's greater than that. Again, no equal to. And I just put my proper word in between. Since the shading's in the middle, I would put the word and. Again, if you want to write it as like a domain or a compound inequality, you could write it as -3 is less than x, which is less than 8. You don't need both, just whichever one you want. All right. And for example 2, we can factor this right away. So that would be what multiplies a -5 adds a -4, -5 negative, or -5 positive 1. And when I set them equal to 0 and solve, I get x is, again, I'm going to put just like an empty box here. X is blank 5, and then x is blank -1. So I do my number line. Zero also, again, happens to be in between here. It's not always going to be the case. I like to test x equals 0. It just makes numbers work really well, but you can test any number. I don't test your boundary point, so I would end up with 0 squared minus 4 times 0 minus 5 is greater than 0. Or -5 is greater than 0, which is false. Which means 0 should not be shaded. So I'm going to put an open dot at -1, open dot at 5, again, just because it's not equal to. If it was equal to, I put closed dots. And then 0 should not be shaded, so my shading is going in the opposite directions. So I go back. Since the shading's in the opposite directions, I can go ahead right away and write or, and then I have to fix my inequality. So this is less than -1, and this is greater than 5. All right. These can be a little tricky, so just take your time, and we'll practice them some more.